Thanks, test. Yeah, I think we're live. Okay, good. Welcome everybody to our talk about private LLMs. Yeah, when ChatGPT is not an option. So before we dive into the talk, let's explain a bit who we are. So I was introduced as ML engineer. I also call myself sometimes an ML solutions architect. So what does a person do in this role? Well, I help clients build and design machine learning solutions, be they classic ML solutions or Gen AI solutions. That's a bit about me. Remy?
I'm Remy. I am one of the principals of the AI cell here at Xebia. And in my day-to-day work, I work as a machine learning engineer, but I do also data engineering, a bit of data analytics, so the whole data package. And today we're going to focus on large language models. So take a step to the AI side, but also talk about some of the engineering aspects of it. As you see, we have beautiful slides, but in the end we are still engineers. So our slides actually look like this. So LLMs nowadays are everywhere and they're really easy to use. Who of you has used LLMs in a hobby project? Almost every one of you. Who of you also actually used large language models in production? As we see, not that much of people, and that's really important and to keep into our minds when we talk about the rest of our presentation. And so we see these LLMs are everywhere and are really easy, and we see a lot of common use cases. And for example, we see it for code generation, our GitHub Copilot. We see it in chatbots, and even advanced chatbots with RAGs, who can use your own knowledge base. We see data extraction use cases. You have unstructured data, and then you use an LLM to find all the data points you search for in the data, and then make a table out of it. For example, searching through contracts, you want to do data analysis, and then you can use the data extraction. But also in our day-to-day life, we see that we use LLMs, for example, for meeting summarization. So we see they're everywhere and they're becoming more and more common. And the one thing that's really nice is it's only a single API call. It's an API call, you create the prompt, do the API call, you get a response. That's it. It's actually really easy to implement. And that's also why we see a really rapid adoption of these tools nowadays. And also integrating in existing tools, which is really nice. But it all sounds fun and easy, but there are also some risks involved. Our observations is that we often see that the ease of implementation, that single API call, also sometimes overshadows the risk. Because if it's so easy, we often underestimate the risks that are being involved when we use this external tool, when we send out this prompt or use an LLM in general. And what we also see is a lot of companies, organizations, they're really eager to implement AI in their processes. And a lot of times we also see Rust implementations. Really want to go live, go into production with this tool. But yeah, it's good sometimes to take a step back and think about the risks that are involved. To do that, we have a very simple framework. The risk management plan. We have 3 steps. The first one is just identify the risk. And it's usually a step that's being overlooked. And so every time you build a new tool, and especially if it's AI, take a step back and try to determine what risks are being involved in your project. The next one is quantify, how big is the risk, and then manage the risk. And management of a risk, there are 2 actions possible. Either you accept the risk, but then again, to be able to accept the risk, you need first to quantify it, because otherwise you don't know what you're accepting. Or you mitigate the risk. You take some actions to reduce the impact of the risk. And with large language models, there are a lot of risks to manage. We have this thing called hallucinations, and where the LLM comes up with things, and we're not sure if that's the right use. We have abuse, For example, when you have customer-facing chatbots, then they're trying to abuse the system, reverse prompting, prompt injection, sometimes low quality of the outputs. Just the LLM is not good enough yet to create the output you would like to have. But also a risk is the use of external large language model providers. And so you send your model somewhere abroad, or to another company, or to another solution, and this also creates a risk. We also have compliancy, for example, with the AI Act. You cannot use AI or large language model for every use case you have into mind. So it's always good to check, does this also comply with the AI Act we have? And there are a lot of other risks to take into account. Today, we're going to focus on this one, using the external large language model providers. And something that I would like that you stick with you till the end of the presentation, but also when you go home, all risks should be managed before going to production. Manage means either accept or mitigate it. So let's take a look at these external LLM providers. So what is an external LLM provider? Well, I think most of you already worked with an external LLM provider. It's an OpenAI, it's Claude from Anthropic, it's Gemini from Google, we have Mistral. So these are all LLM providers that are somewhere else. We also see them as a black box. It's just the API call. You send it, you get something back. But what's happening over there in their systems, you have no clue. And also, most of these providers are also not located in Europe, except for Mistral, of course. So there are certain situations where these external large language models don't fit your solution, or create a too big of a risk. First of all is data residency. So where is the data stored that I send to that other system? And in the EU, we have some clear regulation about, and not always that's clear, with GDPR and the AI Act, that sometimes also states that you cannot store personal data abroad. We also have something with responsibility, because you remain liable for the data. So even if you send your data to an external processor, if the data there is being leaked, you, as the first step in the chain, as the data owner, you are still liable. We have network security, because when you use an external provider, you send all the data over the internet to the other provider. And there is also the challenge of vendor lock-in. Because when I, for example, choose ChatGPT, I only can use OpenAI as a provider. So in the end, maybe OpenAI increases their rates. I have no choice to stick with OpenAI. And so these are some of the reasons, some of the risks that are being involved with having external LLM providers. Yeah, so short summary, usually we see it unsuitable for highly sensitive data, strict compliance regimes, or sometimes when there's really specific customization needed that the external provider cannot give you. All right, so this external provider is not the solution. And now? Do I need to make the decision maybe not to go with LLM? Say, well, this use case we cannot deliver? Or is there maybe an alternative? And this was also some of the questions we are asking ourselves. And we came up with the idea of self-hosting. Well, maybe we can self-host as LLMs and take away a lot of those risks that we mentioned. So let's take a look at self-hosting. Why do we want to self-host? We see 4 major reasons. First one is full control. You deploy your LLMs either on-premise, on a co-location, or somewhere in a cloud that you manage yourself, so it stays within your own virtual network. And you have a lot more control on all the data that's being processed and how it's processed and where it's stored. You can move closer to alignment with compliance. As I mentioned, there we have the AI Act, we have GDPR, but also some companies, organizations also have their own rules regarding compliance. And this allows you to stick to it because you bring it back to your own control. It also allows for customization. When you have run, for example, ChatGPT on OpenAI, you can only use their model. There's no way to fine-tune it or make any changes to it. When you run your own, you can. And in the end, we also have the strategic flexibility, and that ties in with the vendor lock-in. When you host your own model, it doesn't matter where you host it, it's your own model. So all fun and games, that's those self-hosting, but yeah, there are also some trade-offs. There are 3 major trade-offs. The first one is the model choice. You can only use open models. Think about Llama, Gamma, and there are Qwen, and there are a lot of open models, DeepSeek as well, but you cannot use Gemini, you cannot use ChatGPT. So you're limited to those models. Another big point is infrastructure costs, right? Because you need to run those models by yourself. So you need to have these large, beefy machines that can run the models. And you also need personnel, right? You need to have someone who has the knowledge to maintain those systems, knows all the ins and outs, and just make sure the model is running reliable. So there are some trade-offs. And what we see in the end is cost, right? Your personnel incurs more cost. The infrastructure also incurs cost. And what we see in our experiences is that it is at least per token 10 to 100 times more expensive. And so that's something important to keep into your mind. So far about self-hosting. It gives us a lot of opportunities, but it also has some trade-offs. And Roy will tell you a little bit more about that infrastructure and how everything can work.
So Remy mainly focused on why. Why would you be interested in hosting these private LLMs? In my part, I'll focus on the how. So how can we actually implement these LLMs? How can we host them ourselves? And then we'll hopefully shine some more light on why infrastructure is so expensive or personnel is expensive and what things to consider when picking different models. So let's look at the current state of affairs. So most companies nowadays run on hyperscaler infrastructure. So what it looks like, if you're running your agent in production, you have some agent runtime. So I picked as an example GCP. So in GCP, you can use Vertex AI agent engine to run your agent. That agent calls one of these SaaS models that Remy just explained about. And that's basically all you need. You're good to go. You just need to consume that agent in some application, and that's what you need. When we go into self-hosting, we don't have this application runtime. So you need to run your agent somewhere. Now, this is not the most significant choice that you need to make. So for the scope of this talk, I'll ignore that because it doesn't have an impact. But first of all, like Remy said, we need to pick the models. Which model are we going to use for the use case or use cases that we have in mind? Then once we have picked the models, we can't just use these weights out of the box. We need some serving framework. So that's another decision that you're going to make. And then finally, once we have this serving framework, we also need to run our model somewhere because we cannot use the SaaS providers, so we need our own infrastructure. Where is this going to physically run and where do these GPUs live? So let's try to tackle these boxes from top to bottom. First, model selection. you might think if you're selecting a model, if you can't use the state-of-the-art SaaS models, okay, we're going to have a significant drop in performance. So we have very poor models to work with. Well, that might have been the case when we started this whole AI hype, so to call it. In the beginning, the state-of-the-art models were significantly better. But what this graph shows is that over time, the gap between state-of-the-art models and open-weight models is closing rapidly. So nowadays, the performance of the state-of-the-art models is 6 to 9 months ahead of what open-weight models are. So the performance is actually quite comparable. So that's not something that we necessarily need to concern about. Okay, so what are we going to do then? So we just pick the biggest and best open source models, and we're going to run these. Okay, how are we going to run these? Because these models have 250 billion up till 700 billion parameters. That may not say a lot to you, but these models are huge, so it's not straightforward to just host these somewhere. You need dedicated hardware for that. So that actually begs the question, do we need these huge models? Can we actually use something smaller? So if we take a step back and look at, for example, the Qwen 3 model, the 8 billion parameter model, which is 2 orders of magnitude smaller than the models that we just described, this model you can run with only 19 gigabytes of GPU memory. We use this formula at the bottom to compute that, so you can do the calculation yourself. But this runs on a single GPU. So actually, this model you could run on your own laptop. And for some simple tasks, this is actually sufficient. So tasks like summarization, classification, or simple question answering. But maybe the use case we have in mind is a bit more complex. So we go an order of magnitude bigger. So we take a Llama 3 17 billion parameter model. Okay, this needs 170 gigabytes of GPU memory, only to load the model weights, by the way. More about that later. We already need multiple GPUs to run this. So you can already see that the infrastructure needs for this model and the complexity, how to maintain this and how to orchestrate this, becomes more and more difficult. But it's still quite manageable. And with this type of model, we can build simple agents. So what can we do with simple agents? Well, they can do reasoning, for example. They can do planning. They can do these kind of things. And they can help you with challenging creative tasks, like, for example, building a PowerPoint presentation for a conference talk. These models are quite good, for example, for RAG systems, where you don't have to have a complex agentic workflow, but these models you could use there. And then only if you really need it, if you think you want to go there, you're going to deploy the beast. Because for you to run this model, we need more than 1 terabyte of GPU memory. That's a lot. That's, for example, 8 state-of-the-art NVIDIA GPU chips. Those machines, to buy these machines, it costs a lot of money. So a lot of investment is needed upfront to be able to start with these use cases. And you would only need these with complex agentic workflows where you have multiple agents that interact with each other, or an agent that needs to call multiple tools and does complex planning in that way. So what I want you to take away from this part is that if we pick a model, don't just start with the biggest model. Once you go for self-hosting, it's more important to choose which model you use, because it's not as easy to swap it out. And the smaller model you pick, the easier it is to run, so you get a quicker time to value. Okay, so now we know something about how to pick a model and how to deal with that. So let's look at serving this model. And to look at that, I think it's important to look at the use cases that we might want to do with these models, because the use case can determine which serving framework you're going to use, as well as it has an impact on the model choice that we just described. So let's look at conversational AI. Think of a typical chatbot. The pattern of an interaction with a chatbot is you have a system prompt where you explain what your chatbot is supposed to do. And then your user sends a query, and then your chatbot answers that query. Simple as that. But then the user might want to ask another question and another question. So you can see that the input of the model grows and grows with each question that you ask as the chat log is growing. So this in itself is not a problem, but then when we look at the model architecture of LLMs, all LLMs nowadays are transformer models. And at the heart of a transformer model is the self-attention mechanism, which computes a pairwise interaction of all the words in your input to understand the language that you send to it. So what does that mean? This pairwise interaction is a quadratic computation that you're doing. So as your input increases, the time it takes for your model to respond increases quadratically. So the bigger the input, the longer you have to wait for it to return. So what most of these serving frameworks do, they do prefix caching. So they store computed results somewhere in a cache so that we can go from quadratic to a linear time complexity. So we reduce the latency that we need to respond. And when we get back to the use case that I just described, this is where it comes in, because we have this repetitive pattern with conversational AI. We first have the system prompt on a question, and if we cache that, then after that, we only need to do the computation, the quadratic part, only on the query 2 that we get, the thing that we don't have in the cache yet. And we can build out the cache as we go. So we see that the caching is very important for picking a serving framework. So this is not only the case for conversational AI, this is also the case for agentic workflows. So the pattern with agentic workflows is slightly different, but you see the same recurrent pattern occurring. So we as developers, we set a goal. We tell the agent which tools it can use. And then we set the agent at work. So the first thing it does, it's going to plan, it's going to take an action, then it's going to do an observation, and then it's going to plan, act, observe again. So again, we have this growing pattern, and also here, this prefix caching is important. So what does that look like in practice then, if you have a GPU? So in this example, the blue blocks are the memory of your GPU that's taken for only the model weights. Well, we see that almost twice as much is used for your prefix caching. So you don't only need this GPU memory for your model, but you also need it for the cache. There's other ways to deal with this cache, but this just shows how important this caching is in serving models yourself. So what type of model serving frameworks do we have? So VLLM is the most popular serving framework by far. This is very good for these conversational AI and agentic workflows that we just described. Then we have a framework like TensorRT LLM, which only works for NVIDIA chips, because this is developed by NVIDIA. And this is more generic deep learning optimized framework that's less good for these recurring patterns, but is the fastest in computing tensor operations on NVIDIA GPUs. Then finally, we have HGLang, which is a more complex framework to use. I've tried to use it, but the documentation is not very good. The community is smaller than VLLM. But this framework works better for these more complex workflows, and you're able to get more performance, latency, and resource utilization from this framework. So here you see that there's different options that you can pick. Okay, so we have models now, we have serving framework. Where are we going to run our LLM? So in general, there's 3 options that we can pick. First, we can self-host on a hyperscaler. So we're not going to use the SaaS providers, but we're going to run it ourselves on something like GSP. We can pick specialized GPU clouds. It's still a cloud solution, but these cloud solutions, typically, they only rent GPUs to you. Or we can borrow our own hardware and run our stuff on premises. So let's look at each of these 3. So what is the advantage of self-hosting on a hyperscaler? Well, the advantage is you have low capital expense. You can just directly use random machines from them. And probably if you can use this, it also provides an easy integration with your current software and hardware stack, or software stack, of course. The downside is it can conflict with your data sovereignty needs. Also, the availability of GPUs can be uncertain with these providers. And yeah, because they are hyperscalers, they typically offer these GPUs at a premium. So your operational expenses can get quite expensive quickly. So what next then? Well, if that becomes too expensive, we can look at specialized GPU clouds. Again, low capital expense because they buy the machines for you and they maintain them for you. You get quick access to state-of-the-art hardware, and they have a very competitive price. Downside of choosing this is that not all of the providers of these GPU machines, they provide like private link access, which makes it, which can increase latency. And also the services that these GPU clouds offer, they vary widely. So with some you get a lot of managed services, with some the GPUs are less expensive, but you need to do more yourself. So it's a balancing act to pick which specialized GPU cloud you would like to use. And then finally, for people that really want full control, you can buy your own machines and run them on premise. Advantages are, yeah, like I said, you have full control, you run everything, but that's at the same time also the downside. You have predictable cost and capacity, you know exactly what you can run, how much you can run, but you are not very elastic. If you want to scale up, you need to buy a new machine. Yeah, you need to have procurement, you need to install the cooling, install the physical equipment. So yeah, that's the downside. And there's, yeah, like I said, high capital expense, you need to invest upfront. But also your maintenance burden is quite high because you need a specialized GPU operating team to be able to run this. So this is only for the real hardcore people. So how do we roughly distinguish between them? Well, self-host and hyperscaler do that if regulation allows you to. It's your shortest time to value, easiest to set up. Then, if things become too expensive, consider moving to a specialized GPU cloud. And only if you need this full control, so either to push out the most performance out of your resources, or you have strict compliance requirements, then buy the stuff yourself and host it yourself. So yeah, this wraps up our whole architecture stack. We have described all the choices that you need to make. So let's wrap this up. So we've looked at the current situation. So the current situation, the status quo is SaaS models are easy to use. But yeah, like Remy said, they are often picked without considering the risks. There are alternatives. We can self-host our LLMs. It's complex, but we showed that it's a possibility. Then, looking ahead, what do we think the future holds? Well, we think the future does hold self-hosting of LLMs. And there's a few reasons for this. Like we said, the open weights models are getting better and better. So the gap between state-of-the-art models and open source models becomes smaller. And also, like an example, Andrej Karpathy, which is a prominent figure in the world of AI. I think most of you probably know him. He built his own GPT from scratch using a specialized GPU cloud for only $800. So that shows that it is getting more and more accessible for people to build things that state-of-the-art cloud providers build. And similar advances in the field we observe in terms of fine-tuning, where that becomes easier and easier. So yeah, you can run your own fine-tuned model that are fine-tuned on your own domain, for example. So finally, what can we do? Well, we're a consultancy company, so of course we can help you. So as Xebia, we've built this setup ourselves. We had the hardware for some time in our office and played around with how we can self-host our LLMs. So we know how this thing works. Also, what we've not discussed this talk is the whole LLM ops cycle. So how are you going to manage your agent, observe it, see what's going on? We can help you design and implement your LLM ops stack. So yeah, consult us to be your sparring partner to reduce complexity and provide you with a clear and reliable path to value. Thanks.